Projectile motion in a resistive medium. It refers to the motion of a projectile through air or another medium while experiencing a resistive force. This resistive force often depends on the velocity of the object. Unlike the ideal projectile motion, which ignores the air resistance, this type of motion results in trajectory that differs from the classic parabolic path with a shorter range and a reduced height due to the energy loss caused by the resistance. Let's see the difference between an ideal projectile motion and a projectile motion under resistive medium through graph. Here, the blue line represents the projectile motion in vacuum and the red line represents the projectile motion in a resistive medium. Here we can see the range difference and a small height difference. Compared to the projectile motion in vacuum, the range and height of the projectile motion in a resistive medium is reduced. Next, we are going to discuss about the force which causes the reduction in the height and the range. The first one is the gravitational force. This force acts downwards and is constant. We can represent gravitational force as Fg is equal to mg, where m is the mass of the projectile and g is the gravitational acceleration. The next force which influences the range and height is resistive force or drag force. This force opposes the projectile motion, acting in the direction opposite to the velocity. Its magnitude can vary with velocity and shape of the object. For lower speeds, it is linear velocity, which is F drag is equal to minus kv, where k is a constant and v is velocity. For higher speeds, it is quadratic in velocity. We can represent it as F drag is equal to minus cv square. C depends upon the medium density, the object cross-sectional area and its drag coefficient. Now, the equations of motion along x and y axis in the presence of air resistance. The difference in the x and y axis is that the drag force slows down the object in both directions, but gravity only pulls it downwards on the y direction. We can represent this as in x axis, as we know, by Newton's second law, F is equal to ma, where a is the first derivative of velocity, that is dv by dx. So we can write that m dvx dt is equal to minus f drag x, and in y axis m dvy by dt is equal to minus mg minus f drag y. F drag x and F drag y are the components of drag force along the x and y axis. Next is terminal velocity. Terminal velocity is the constant maximum velocity a projectile reaches when the resistive force due to the medium, that is air resistance here, equals the gravitational force pulling it downward. This equilibrium results in zero force, meaning the object stops accelerating and falls at a steady speed. We can represent it as mg is equal to f drag. Next is application of projectile motion in a resistive medium in ballistics and sports physics. So, what is ballistics? Ballistics is a study of object in motion, specifically projectiles like bullets, missiles, and artillery shells. In ballistics, understanding projectile motion is crucial because it helps to predict how these objects will move when fired or launched. When a bullet or artillery shell is fired, it does not move through vacuum. It encounters air resistance, which affects its path. The drag force from the air slows down the projectile and alters its trajectory, especially over long distances. Without accounting for air resistance, it would be difficult to accurately predict where the projectile will land. It is also important in military and defense applications. And in sports physics, the motion of ball and other objects through air is essential to gameplay. For example, in baseball, golf, or soccer. Understanding how a ball move help player and coach to improve performance. When a ball is thrown, kicked, or hit, it experiences drag just like any other projectile. In addition, certain sports techniques involve adding spin to the ball, which can change its trajectory due to the Magnus effect. Air resistance and spin can greatly affect the ball's path, speed, and behavior in the air.